In this chapter, we are going to take a look at function notation. We're going to go through the whole gamut of function notation. So some of this is going to be completely something you've done before, and then we're going to get to some things that maybe you don't remember. But we're going to start out with the basics of what is a function. We're going to look at function notation, and then we're going to be looking at graphing some specific functions, and then also just some story problems with function notation in it. Again, just to make sure that you are as comfortable as possible with functions. So for a function, for each input, there is exactly one output. So I can't have an input of 5 and have two different outputs. There can only be one output for each of the inputs. But the reason that we say for each input is because we don't have necessarily all the different values. It might be discrete. We might not be able to have decimals, so that might just be points. Or based on a story, we might have restricted domains, all of those different pieces. So that's why the definition is for each input, there's exactly one output. So these are just some basic examples, and then ways that you can see it. So in the first one, we could just look at ordered pairs. So I have an input of 6. Its output is 12. I have a different input. I have a different input. I have a different input. So for each of these, since it's a different input, they don't have multiple outputs. So is this a function? Yes, it is. Whereas in the second one, for an input of 5, I have an output of 20. And then I have an input of 5, and I have an output of 25. Since they are two different outputs, this is not a function. And again, it happens here as well. I could look at a mapping. I could look at a table of data. And so again, 1 goes to 2, 2 goes to 4. So each of these inputs are different, and they all have an output. Now, 1 could have an output of 2, and 2 could have an output of 2, and 4 could have an output of 2. As long as it didn't have any of these other ones, they all could have outputs of 2. That's still a function, because for each input, there is exactly one output. So yes, C is a function as well. Over here, I have an input of 4, and it goes to 2. It has an output of 2, and it has an output of 6. Therefore, no, this is not a function. We can look at our linear. I could graph this. I could look at a bunch of data points. And yes, this is a function as well. And the same thing with the square root. If you don't remember a square root function, it looks like that for its parent. And again, for each input, there is exactly one output. So yes, this is also a function. When we have pictures, these are super helpful for us because what we will look at is we will look at the vertical line test. In our vertical line test, if we draw a vertical line and it crosses our function at most in one spot, so I draw my vertical lines, it only crosses each time at one point. Same thing here. This one, as soon as it intersects the function twice, that it fails the vertical line test, therefore it's not a function. Because this would be, for instance, the point 1, 2, and this looks like it's the point 1, 8. For one specific input, there are two different outputs. Therefore, yes, yes, no. Sideways parabola is a typical one to look at. Fails the vertical line test right here. It passes it right here at that sideways vertex, but it fails it there. As long as it fails it in one spot, it is not a function. Function notation can be written slightly different, so making sure that you understand the different forms of function notation are important. You're used to f of x, but there's also this notation which means f maps onto. So therefore, one notation that you might see is this f colon arrow 2x plus 7. That is exactly the same thing as f of x equals 2x plus 7. So these two are equivalent to each other. So if you see this top notation, don't be afraid to write it this way. You do not have to use this top notation, but you have to understand it. So if IB gives you a question, they may give you this notation, and you can absolutely write it this way just for comfort. They will not take off anything for it. So these are 5 different problems that work with function notation, just getting you to practice it. Again, nothing too spectacular. Why don't you pause me for a minute and go ahead and do each of these 5 problems. So in the first one, f of negative 1, substitute in negative 1 for x. Therefore, it's negative 3 times negative 1 squared minus 1. And then simplifying this down, you get negative 1 times 1 minus 1, which is negative 4. Therefore, f of negative 1 is negative 4. So we're going to do the same thing for all of those. B, C, and D are both exactly the same. E, we're going to have to simplify. So f of 0 equals, this one's nice because 0 squared is 0 times negative 3 is 0 minus 1. So that one's just negative 1. F of 100, or yeah, f of 100. So substituting in your 100 for x squared, so that's negative 3 times 10,000 minus 1, which is negative 30,000 minus 1, which is negative 30,000 and 1. Plugging in A, for that one, it's just like plugging in x. So f of A equals negative 3a squared minus 1, and you're done. That one's nice, short, sweet. So now I have a values instead of x's. That's it. It just interchanged the variable. And then in the last one, x plus 1 is now my input. So into my equation, that's negative 3 times x plus 1 squared minus 1. So for this one, be really careful. Make sure that you are doing your algebra right. So what do I do first? Multiply or square? Hopefully you're all thinking square. Exponents first. So x squared plus 2x plus 1, and then that's minus 1. And then hopefully you're remembering you multiply next, so it's negative 3x squared minus 6x minus 3 minus 1. And that's negative 3x squared minus 6x minus 4. Really common to lose this minus 1 at the end after you do this expansion, so be careful. Make sure that you have everything there. The next two problems are story problems based on function notation and actually getting you to understand what are they telling me here. So I'm going to explain in words. I'm not going to write it down. And then I'll calculate its value for both A and B. So the formula to calculate the volume of gas left in a car's tank in liters after traveling d kilometers is as follows. So in part A, it says explain what V of 250 means. So 250 is in place of D. So think about, what does 250 mean? Well, that means we've traveled 250 kilometers. We're trying to find V of 250, which means we're trying to find the volume of gas left in the tank after traveling 250 kilometers. So then when I calculate that, V of 250, that is negative 0.115 times 250, because again, that's your D value, plus 60. Type that all into your calculator, and you get exactly 31.25 liters. Since that is exact, you absolutely can leave your answer as it sits. If it was approximate, if it kept going in your calculator, you'd have to round that to be 31.3. So B says explain what V of D equals 10 means in the context, and then calculate the value. So now V of D is 10. So V of D represents the volume of gas. So what we're looking at is, when do I have 10 liters of gas left? Like, how many kilometers were we traveling to get to that point? That's what we're looking at. So therefore, 10 goes in for V of D. That equals negative 0.115 D plus 60. So subtract the 60, divide by negative 0.115, type that into your calculator. And D ends up equaling 434.78, etc. Rounded correctly, that'd be 435 kilometers. And then C says what values of D do not make sense for this. So again, thinking about what D means, D is how many kilometers we're traveling. So therefore, what we have left, so D has to be greater than 0, because we're traveling for more than 0 kilometers, but it has to be less than or equal to some specific number. I'm going to call it n, but I have to define n. N is just the distance that can be traveled on a full tank. So we have to define that because we introduced a new variable. So we're probably not going to run it out of gas, okay, or in this case, gas in liters. So that's why it's going to be greater than 0, but then it has to be less than however many total that we can drive. Second story problem. Nikita's planning a sport banquet. He must pay $320 to rent the room and $20 per person for dinner. Express the total cost as a function of the number of people who attend the banquet. So they're telling you which variables that we're using. So therefore, my cost depends on how many people attend, so therefore we're going to find C of n. So C of n equals, no matter what, it costs them $320 to rent the room, plus $20 per person, so 20 times n. So in B, what notation are we going to use for 125? So that's C of 125. Calculating that value, plug in 125 for n, so 320 plus 20 times 125. So the cost would be $2,820. Moving on to C, what notation can be used to find the number of people who could attend if his budget is $1,250? So now I'm giving you $1,250. That is the cost. Therefore, $1,250 equals the cost. So C of n. So my formula then, 1,250 equals 320 plus 20n. So subtract the 320, divide by 20, n equals 46. So we can have 46 people if he has a budget of $1,250. And the last one, very similar to the last example that we did, what values of n do not make sense for this problem? So n, again, is the number of people who are attending the banquet. So, I mean, I guess nobody could come. Maybe there's a snowstorm or it's just too expensive, whatever it is. But it has to be less than or equal to A. And what does A represent? A is the capacity of the room, so the max capacity. So again, just thinking logically, yes, you could say n is greater than or equal to 0, and in Algebra 2 we would have left it there. But now we're bringing in one more piece. We have to think through this on both ends. We can't have more people than what the room can hold. The last part of this is going to be graphing with functions. So we're going to be graphing functions based on information. Again, some of this is super easy, others of it's a little bit more challenging. So go ahead and pause and graph all 4 of these. So for the first one, we just have 2 points that are there. So through those 2 points, we draw our line. Here, I was able to find a bunch of points based on the slope. Here I had to find the y-intercept and then use my slope. Here I had to count my y-scale by 5s, y-intercept at 40, and then use my slope. So those are just all linear functions that you're super used to. Now here's one. It says use your graphing calculator. So you absolutely can use your graphing calculator to sketch these graphs, but I'm hoping since you've already gone through Algebra 2 and we've done transformations with this, you can graph these with transformations. So if you know how to do this with transformations, pause it, go ahead and do it. If you don't, I will talk through how to do all the transformations. And then if you did do it, then just check your answers. Okay, so the first one is a quadratic. It's shifting up 4 units because it's not inside with the x. So it shifts up 4 units. And then this is negative. That's the way it opens. So this is going to open down. Otherwise, the a value is 1. So therefore, it's 1 over and 1 down. And then it's 2 over and 4 down. That's how our parabolas typically go. Usually goes 2 over 4 up, etc. So there's our quadratic. That should be more U-shaped, not so much V-shaped. And this is a square root function. Remember, square root function goes like this. Since the minus 3 is attached to the x, that's shifting left and right. It's always the opposite of how it affects your x. So we shift that starting point 3 spots to the right. Then it goes 1 over 1 up. Then it goes 4 over and 2 up. And then it could go 9 over and 3 up, etc. So there's our graph. So again, just taking a look at what type of functions we have. And then we're going to move into domain and range next.